No,
yeah, inside. Okay, going back to our analogy here, everybody. Okay, so our atom is the size of a football stadium. Okay, the nucleus is a marble in the middle. Inside the nucleus are smaller things, so here's kind of a visual. It's quite wrong, but it'll give us started. Okay, inside the nucleus are two things called protons and neutrons. Okay, protons are positively charged. Neutrons are neutrally charged. And what's interesting is that marble of the football stadium makes up most of the mass. So the size of the volume is the size of a football stadium, but the marble is crazy, crazy dense. They give the analogy in this video that the density of a nucleus is analogous to taking a 1 by 1 by 1 foot box and filling it with the mass of every car on planet Earth.
Whoa.
That's how dense that marble is.
Holy density.
Okay, that, yeah, right, like insane amount of mass. Okay, because what's interesting is the electron.
Sweat just like all over your face.
It's like break the.
Have practically nothing.
Yeah, so they're negatively charged, okay, but in terms of mass and size, electrons are almost nothing, right? It's kind of like that problem we did with sig figs last time where we added a number but the number didn't change. That's like how it is with taking or adding electrons from an atom. Is the mass of an atom doesn't really change because they're so small in comparison. They are about 1/1000th smaller than a single proton. That's why if our nucleus is a marble, you can't see the electrons because there's protons in the marble, and then you got to cut that proton up into 1,000 pieces to get the mass of an electron. And then the rest of the atom is just empty space. So that entire football stadium is literally just empty. Which is so bizarre because last I checked, that didn't feel very empty. Right? Like, I don't feel empty. So why do things feel solid to us? We actually do feel pretty empty. Aiden. Yeah, it's just the scale is insane, right? Between atoms to us. Now, the other thing that is really the big part of it as well is the electrons aren't stationary, right? So we have this giant football stadium where the electrons are, it's all empty, but the electrons are in constant, super fast motion. So really a lot of what we feel is actually electromagnetic fields because they create and they fill the space even though there's really nothing there. I think it very similar to like if you watch a fan spin, right, and it's on fast, it looks like the fan is everywhere, right?
Yeah.
But it's not once you stop it. That's kind of how electrons are. Is they look like they're everywhere because they're moving constantly all the time.
So these are like
technically like pierce like
everywhere. So like if you move like fast enough, you could like stop it and put your head like in the middle of it.
So theoretically, for sci-fi fans, like if you could control the speed of electrons, right, you could like go through something.
OMG.
Because it's mostly empty.
Oh yeah, I've like seen TikToks of like people like you can just keep touching a wall like maybe at the perfect moment you could like go through it.
No.
If you try to set up an experiment to observe
I was like,
the
what?
of the electron, the electron will change its behavior.
Because like everything could be
Maybe, I guess so.
or like something super small like a moon.
Yeah, I guess in theory you could.
But like it's
You'd
not.
have to have like a needle made of like quartz.
Let's reverse it and then start.
I guess like
This video is gonna be so involved. We're just gonna do a conversation between nothing else in the Oh, there's like actually.
Do you think they can hear us?
Oh, they can probably hear us.
Yeah,
I'm going.
Comment down below on your favorite part of the video.
Remember to share with your friends.
What's up?
Okay, focus back on friends, everybody.
Yeah, just comment and subscribe.
Alright, so now let's kind of take this picture of an atom. Now once again, this is how we model them. And there's things that can be learned from this model. Even though it is quite wrong when you go to size and proportions, right? Because if this is the size of a nucleus, these are not electrons. But there's still things that can be learned, and I still want you to have a visual in your head. Okay? So let's break down how these things are all connected. So protons we said are positively charged, electrons are negatively charged. So those two things come together to determine the charge of an atom. Whether that atom is neutrally charged or positive or negative. So if it is neutral, then protons and electrons will be the same. But we'll see in a second, if it's not equal, then electrons have changed. Key thing is that protons are the DNA of an atom. You change how many protons something has, and you change the element. That's why this number on the periodic table is signifying only protons. It could be other things too, but it is never guaranteed to be anything but the proton number. Because if something has 47 protons, it has to be silver. If it's silver, it has to have 47 protons. That's the only thing that has to be true. Electrons and neutrons can vary within an atom, and it can still be silver. Okay? Fun fact, we won't learn about this, but just so you know, there are actually things smaller than protons and neutrons. If you've never learned that before, scientists now know that those can be broken down into things called quarks. There are 6 different types of quarks, and there's different combinations of them that make up protons and neutrons and other things. So, anyways, if you choose to go and study quantum physics, that's what you'll get into. And yes, the idea of the quantum realm is not, okay, going to the quantum realm, I don't know about that, but the quantum realm is the real place, like in terms of that things are that small, right, past an atom. Okay, now, atomic number is the number on a periodic table, so if you want to draw, there's a picture on your notes that kind of got printed up top of a little box of carbon. And if you want to label that this top number right here on the periodic table, it's called the atomic number. And that tells you once again how many protons something has. Okay? This number down here, which on my periodic table is red, is known as the atomic mass. We've also learned that it's the molar mass of it. Now what's significant here when we talk about the structure of an atom though, is it is an average mass for an element. It is not the exact mass for a single atom. It's an average of all the atoms of that element in the universe combined. To know the mass of an individual isotope or element, that is known as what is called the mass number, which is just straight up protons plus neutrons. Okay, protons plus neutrons gives you the mass number. Why do we not include electrons? They're big, right? We would add it in and then by sig big get rid of it, right? Doesn't really change it. Okay? But this is very important. This is not on the periodic table. What's that on the periodic table? The average. So this, and we'll do the calculation today, this is determined by averaging all the mass numbers that exist. Now we'll look here, it's actually a weighted average too, because not all isotopes are created equal. Okay? Now an isotope is proton or atoms of the same element with different masses. Okay? So these are examples, these are isotopes of carbon. Sometimes carbon weighs 12, sometimes it weighs 13, sometimes it weighs 14. It's all carbon, it all looks the same, it would all smell the same. To us, I mean, you wouldn't want to eat it, but it would all taste the same. Right? Like, we would not be able to tell the difference by looking at it or analyzing it in any way. Because the only difference is at a very, 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 very small level, this one has 2 more neutrons than that one does. But neutrons do not affect chemical behavior. Those are electrons. Neutrons just make things heavier. Now they do affect whether something is radioactive or not, which is once again kind of a different route of chemistry, of nuclear chemistry that we won't talk about in this class. So for our sake, like, you wouldn't notice a difference. Yeah, Aiden.
Doesn't
Until
adding
you get cancer.
protons to an element make it a different element?
Did I say protons?
Yeah.
I meant neutrons. Thank you. Yeah, so the proton number doesn't change, right? They're all carbon. They all have 6 protons, but we're just changing the mass number. Okay? So this right here is known as isotope notation. Right here where you list the mass number and the symbol. The bottom number is obviously the atomic number. And this one is kind of optional. It's not really necessary. Why is it not really necessary to put a 6 there?
Because it's always going to do this.
Yeah, because carbon can't have anything but an atomic number of 6. So on your homework today, you can decide. You can put it there if you like it, but I often won't because you don't see it. Okay? So once again, isotopes are elements for the same element, but they just have different masses. Okay? All right, let's look at the table here. Flip your page over to the back. So this one right here. Not the home. It looks just like the homework, but this is our example problem. And let's kind of piece all these things together. Okay? All right, I'm going to do 2 of them with you, and then I'm going to have you try the other ones with your table buddy for some smiley faces to see how we're doing. Okay? So the goal here is given a piece or pieces of information, using the periodic table, you can fill in the rest. Okay? The objective here is to see how all these things are connected, and once again, in a very logical way. So, starting with the first one, they tell me that the isotope is chlorine-37. So my first thing is, well, it's chlorine. Go to the periodic table. Chlorine has an atomic number of 17. Okay, so you want to make a note. Atomic number, right, comes from the periodic table. The atomic number is a 2-for-1 deal because it also tells me proton number. Right? This and that will always be the same because that's just by definition what it is. All right? So that's all the periodic table told me. So I go back to the name, and the name is telling me something else. What's the 37 telling me?
The mass number?
The mass number. I think it kind of like wrestlers, because isotopes are named by their weight. And like in wrestling, you're designated by like what weight category you're in, right? So we designate the name with its mass number because I can't find that on the periodic table. What does the periodic table tell me? What's the red number up there?
35.
Yeah, what's that tell me?
It's an isotope.
It's just the average of them, right? We need to know exactly which isotope we're dealing with to be able to fill this in. So it could be close to it, which 37, close to 35. But if you go there and pull that red number, there's a good chance you're going to pull the wrong isotope. So recognize it's going to be given somehow. Okay? Yeah?
Could it be that it's the number, since it's the mass number, wouldn't it mean that it has 20 neutrons and 17 protons?
Good. So the mass number is equal to protons and neutrons combined. Because electrons don't really weigh anything. So to get the neutron number is you can take the mass number and subtract the protons. That's a symbol for a proton, by the way. You put a little p with a plus sign instead of writing the word out. The mass number, okay, mass number minus protons gives you neutrons. Okay, electrons. What are electrons linked to? Protons and the charge. If there's nothing to show, then the charge is just 0. It's neutral. If it's charged, it will show it somewhere. Okay, there's a variety of ways, but it will show it to you. Otherwise, it's 0. So if the charge is 0, then the electrons must be the same as the protons. Okay, so electrons will equal protons if charge is 0. If the charge isn't 0, then we'll see how it can vary. But yeah, Sophia,
How would you write the nuclear symbol?
oh, thank you, I forgot that one. So nuclear symbol, we're gonna do Cl. You have to do the mass number, and then you could do the bottom number, but you don't have to. And if it had a charge, we'd also show that, but it doesn't, so that's all we need. Thank you, I forgot about that box. Other questions? Yeah, Michael?
Is that a dash or a minus in between?
A dash. Good question. That is a thing in chemistry. Yeah.
To get the number of neutrons, it's mass number minus proton, right?
Correct.
Okay.
Yep. Any other questions before we do one more together? Okay, skip down to this one with magnesium. We'll do one with a charge as an example together. Okay, so this one gave me my symbol, magnesium 25, 2 plus. So my first step is go to the periodic table, find magnesium.
12.
Has an atomic number of 12, which means my protons are 12. Okay. The symbol is also telling me the mass number of 25, which now, since I know the mass and I know the protons, I know neutrons must be 13, because those combine to make the mass. Okay? The symbol's telling me that this atom has a 2 plus charge, or positive 2 charge. So it's not neutral. The way I think about it, go ahead, Grant.
Does that mean that there's just 2 less electrons?
Yes. Or 2 more protons, however you want to think about it, right? Because if protons are positive and electrons are negative, this means it has 2 more protons than electrons. So that means electron count would be okay, so that's how the charge links to protons and electrons. And then for the name, we would write magnesium. You gotta do the mass number, and then if it has a charge, we just put it up top like so. Questions on this kind of weird chemistry Sudoku thing going on here? Okay, let's have you try the other 3 problems, and you can work with your table buddy, and then we'll check it for some smiley faces. Okay, ready, set, go.
I smiley time. We can check it one.
Bro, iron.
Oh wait.
8?
Oh wait, 15. That's awesome.
No. Atomic number.
Yeah.
8. No. No.
I'm pretty sure it's oxygen.
What? It's oxygen. Yeah, the atomic number is 8, which
Oh,
means it has 8
8.
protons, which means
What number? We just didn't look at which
it's
one.
oxygen.
Oh.
Oxygen.
You got it.
So oxygen, we know that would be that number.
You have to okay, and then
15 plus 16 is 39.
Try those ones out. So the whole box, I already finished the whole
And
box.
atomic number 15
And then we'll check it here.
is a P. Phosphorus.
So that means we are now working with
Get labeled that
oh,
way.
oh.
This is numbers.
Oh, 3
Yeah.
They're rough.
Yeah, that looks right.
Oh, the charge is
This is basically just Sudoku.
Yeah.
How do you say it?
Yes, there's like a
I think it's just this one.
yeah, Amy. So what does the mass number tell us? Good. So how did you use the mass number? There you go. So what are you gonna add? Yep, because electrons don't really have mass, right? So good. Technically speaking, in chemistry, we actually write it after. It's a way of showing the difference between because there's a difference between saying like, hey, this is a charge versus like in math if you get like an actual molecular value. In big picture, I don't really care, and they won't mark it wrong. So yeah,
Yeah, I know. That game.
the charge, the same piece of charge is net. Yeah.
Did you actually say
Just so that, because I think of it as like
I don't know, I've
that's
never played Persona.
If by chance, I'm going to give just a few people another minute, but if you're done, you can flip it to the front and you can start on the homework while you're waiting.
Like they would just say, let's go and see.
Maybe it's because it's a box designated.
Having the camera right here recording every conversation.
I know, they probably think that was so weird.
See, we're probably going to come back to this video later on to study, and we're going to hear ourselves saying these exact things.
Like, whoa, that's so weird.
Whoa, I have a voice? S and who on earth is S?
SN is...
That's antimony.
Or is it...
Oh wait, no, SN is 10, you're right. No, SB is ant. I think that's what it's called.
I'm gonna check that later. What? Yeah, same. It looks as a 0 and it means that grade 10. I know, my dad was like, what is this? I was like, I promise I'm gonna get a 0.
I'll look around the door. We're almost done while you're doing our homework.
It's like this.
I'll at least tell you your score. Or maybe I'll just, I keep it in Canvas, but then when it's due, people will actually take it.
Programs to do this for us.
I thought I would just like,
Wait, when did you have to write the
A 94 again.
-3 on this one? Oh, you did.
They changed it back and I'm gonna cry.
I got it.
look, I'm telling us.
I was like, yeah, surviving off of a lot of 93.0 ones last year. I know, so now I have to actually get like 94 and
Well, I'll change mine back because that's what my disclosure says.
I'm gonna do that one.
So we got 1, 2, 3.
Okay, I'll give you 10 seconds to finish the thought you're on, because I know you're like, wait, I might be writing this thing down, and then put your pencil down for me. All right, I think we're on the right track. I was glancing at everybody's, and it seems like we're good. I want to check some of them just to make sure we don't have any misconceptions moving forward, and so you can earn some smiley faces. So we're going to check the very last row. Okay, the smiley face boxes are going to be, I'll put stars in them. So this one, and this one, you can earn smiley faces. Okay? Okay, so you should have a mass number of 31. We should have a charge of
minus 3.
And then just to check it, so this is phosphorus, 31 minus.
Yeah, no.
Questions?
So I did -3 and also on the chart from that one.
This is 2 minus, yeah. So it doesn't, big picture doesn't really matter. But notation-wise in chemistry, we do write charges after numbers. So that's how you'll see me do it, because it's just the habit of doing it. That one just got typed the other way.
Oh, so the fourth one is the on the charge is the one go down. I mean, for essentially the fourth one, the one that's already there.
This one?
Yeah.
Yes.
Is that negative?
Yes.
Okay.
Yeah. So once again, I don't really care where you put it. Once again, the technical way in chemistry is to write charges after numbers, because it shows the difference between, hey, this is a charge on a number, not a value of negative. Because there's a difference to mathematically say, like, hey, this is -2 versus this is charged negatively 2. But you're not going to get docked if you put the negative in front. But any other questions on this? Okay, last thing, and then the rest of the time you can just work on your assignment, is talking about the equation and how that red number was formed or determined. Okay, so the atomic number, like we mentioned, is an average, but the key thing is, first off, it is a weighted average. It's not a true average, because true averages, you add them up and divide, right, by however many you have.
We get smiley faces for getting the questions right.
Yes, so for those three, this number, and that number, you have up to 3 seconds. Okay, let's get rid of this here really quick. Good idea. Okay, so you don't need to know these numbers, but just kind of the history behind it.
Why did you say 112?
So what they found, or what they determined, everyone, is carbon-12 was actually the standard atom they used to build the scale. Because once again, all units are just relative to something, right? Like the gram was literally just something that someone decided, hey, this is how much a gram is going to be, right? Same thing with a foot, right? Once upon a time, it used to be the king's foot, was actually how long a foot was, but then when the king changed, that was annoying, so eventually someone decided how long a foot would be, right? So same thing is with atoms. They use carbon-12 as the standard to determine the breakdown of the rest, okay? Now, to calculate that weighted average, this is the equation we use. Okay, so fill this in that box right there. Now, this equation is not on your formula sheet, but honestly, I don't know if you'll have to use it on the AB test. You could, but when you take a test, they're going to give you. But that's not a bad idea to make a section on there that's like, hey, other formulas to memorize. That's not a bad idea to put in, so you kind of all in one place. But honestly, I don't, in like the past 3 years I looked, like they haven't used this actual formula. So we're learning about it today really just to understand this number, because I've seen questions that like the understanding of how this works, but actually doing it isn't really necessary because we already have all the average masses. So if like a question says, what's the average atomic mass of magnesium? You don't have to do this, you just look right there. Oh, it's 24.3, right? But it is important to understand how that number came about, because it does help you better understand what isotopes are. Okay? Does everyone have this written down? Actually, I'll leave it up. Turn back in your homework and go to problem 12, and we're going to do this one together. Okay? So the way the formula works is pretty straightforward. All we're doing is we're just taking the data for each of the isotopes and finding the weighted average. Now, once again, key thing is it's a weighted average. Because in problem 12, we're talking about magnesium 24, magnesium 25, and magnesium 26. Normally, If I were to average these three numbers, what would you get? 25, because an average goes in the middle. But I look at magnesium, the average is 24.3. That's because it's a weighted average based on how present each of the isotopes are. So that's what this percent abundance is telling us, is it tells you, hey, in the universe, almost 80% of the magnesium is magnesium 24. So our average should reflect the highest percentage isotope, okay? So all we're doing in this problem is just kind of checking it to practice the equation. So we're going to take the mass of our first isotope, so it's a big long number here, so it's 23.985042. And I'm going to multiply it by its percent abundance. So it has a percent abundance of 78.99. Now you do have an option. If you want to change all your percentages to decimals like you would normally do in math, you can. You just don't divide by 100 then, if you change them beforehand. So just kind of up to you how you like to plug things in. Okay, so this is for my first isotope. So then we're going to add the next isotope in, 24.985837, times it by its percent abundance of 10. And then our last isotope, 25.982593, times 11.01. Do that all together. Okay, once again, order of operations, make sure you do all the top, and then divide by 100 if you didn't change them already. Okay, once you get that written down, go ahead and try plugging it in and see if you get the answer of 24.31. If you don't get an answer of 24.31, then we need to figure something out. That's what you should get.
Go to my sig thing calculator.
More likely. Once you get 24.31, which tells you you're plugging it in correctly, then you can just keep working on the homework with about the 10 minutes we have left. Okay, but make sure you can get that number just so we can fix anything if we need help.